In this module, we're going to do an introduction to compensation. My name is Christopher Lazarski, and I am the director of the Flow Core at Children's National Hospital. This module will explain what is meant by compensation and how to set up compensation on our instruments. Currently, we have Beckman-Coulter Cytoflex instruments. Some terms which we will discuss include spillover, spread, as well as some of the mathematical subtraction formulas which happen during compensation, compensation matrix, and general signal versus noise for fluorescent markers. Some topics which we're going to discuss include understanding, again, the math which underlies compensation and how to optimize gains in order to minimize spillover. So why do users need to know and understand compensation? Compensation is an integral part of flow cytometry. Once you have more than 3 colors on a flow cytometric panel, you will most likely have to place markers on certain neighboring channels. This will result in spillover. This spillover then will require compensation. It is important for a user to know what to look for with your data to understand what data may look like if it is under or overcompensated. Reviewers would expect an investigator to present accurate data and to be confident in the identification of any subsets using multicolor flow cytometry from compensated data. And this is your data. It is important that a user understand their data and understand the results that they have collected. Compensation ultimately is math to identify the true fluorescent values of a particular fluorochrome. A fluorochrome will emit light, and it will emit light across a broad range of wavelengths, not limited by the detector which you are looking at. For example, here we have FITC, which is detected in the first channel centering on 530 nanometers. However, the FITC molecule emits light all the way out to 650 nanometers. Some of this light then spills over and is detected by the neighboring PE channel. Compensation is an algebraic formula to subtract this spillover in order to report the true intensity of the channel of interest. For PE, we have a certain fraction of the FITC spilling over and being detected by the PE channel. In this example here, we have a percentage of possibly 12% of the total intensity of FITC being read out in the PE channel. This is the spillover into PE. Now, spillover is an inherent feature of the instrument, which is an interaction between the fluorochrome and the filter sets. To arrive at compensation, we have to then start measuring photons and converting this readout to numbers. This is why the gains used during collection have the greatest impact on compensation, because the gains will alter the relative background intensity and the peak intensity in each channel. On this page is an example of the compensation matrix array, which the Cytexpert software can create after compensation. This is to help understand their layout. The main channel to identify the true intensity of is displayed on the left, here FITC. Cytexpert also includes an autofluorescence coefficient. Across in rows, all of the numbers are the spillover coefficients, which have been calculated during single color collection for the compensation. For each channel, the coefficient is then applied to the intensity measured in all of the neighboring channels. We finally arrive at the compensated value of our main FITC channel by subtracting these calculated numbers. For FITC, this would mean the measured intensity of FITC has autofluorescence of 8.69% subtracted, followed by fractions of per-CP, APC, APC Fire, VioBlue, LiveDead Aqua, and PE. Cytometers will automatically create compensation. They will auto-generate these matrix tables, and they will then perform the compensation for each individual cell as it goes through the instrument. Because compensation is a post-acquisition formula, the raw data is not affected, at least on the modern instruments that we are using here. However, we have found that FlowJo can sometimes have difficulties in applying compensation after the fact to data collected on the Cytoflex instruments. This is because of challenges that FlowJo has in dealing with the height versus the area measurements that the Cytoflex exports. Changing the compensation can help improve the appearance of your data, but it cannot recover data which has been collected with gains which were not adjusted to correct for spillover. Additionally, there are some spillover artifacts which are inherent with the instrument and the fluorochromes used, and we're going to discuss that in the next slide. This type of spillover spreading error is not able to be corrected by compensation. On this slide, we have an example of what some errors in compensation can look like. And this is the example. Suboptimal compensation can suggest both false positive results as well as overly negative results. In this example, we have CD56 PE-Cy7 on the x-axis, and we have CD3 per CP-Cy 5.5 on the y-axis. Now, there is a lot of spillover, naturally, between per CP-Cy 5.5 channel and the PE-Cy7. If we apply a spillover percentage of per CP into PE-Cy7 of 50%, that is too much for the gain settings which were used to collect this experiment. This overcompensated data means the CD56 PE-Cy7 signal has too much subtracted from it, and it ends up being negative, significantly below zero. Conversely, if we set a spillover percentage that is not enough, in this case 30%, not enough of the per CP-Cy 5.5 stain is subtracted away from PE-Cy7, and this results in a CD56 signal which appears to be double positive. It appears to be both positive for CD56 and for CD3. Our just right Goldilocks compensation is somewhere in the middle. In this calculation, it was 43% spillover between per CP-Cy 5.5 and CD56 PE-Cy7. This slide is to demonstrate that sometimes autocompensation may end up slightly over or under compensating your data, and small adjustments to the compensation might be necessary. Depending on the channel, these adjustments might only be up or down 5%. In discussion of the suboptimal compensation between per CP-Cy 5.5 and PE-Cy7, the graph with the CD56 PE-Cy7 showed a wide spread similar to a trumpet or a fishtail when graphed against CD3 per CP-Cy 5.5. This spread is inherent in the machine and these two fluorochromes. Compensation cannot reduce the appearance of this spread. The reason for this is complicated, and Mario Roederer discusses some of the issues behind this in publications in flow cytometry listed below. Briefly, this spread is a result of detection of multiple fluorescence signals within the same detector and measurement error which builds up as the photons are counted and converted into numbers. Some color combinations will always result in X versus Y plots with this kind of difficult spillover and spread. Some of the combinations include per CP-Cy 5.5, PE-Cy 5, and PE-Cy 7, along with some of the brilliant violet 605 and 660, as well as Alexa 700, APC A750, and PE Dazzle. Because this kind of spread is inherent in the instrument and the fluorochromes used, The only way to correct for this is really to modify the panel design in the first place to avoid choosing markers which would have co-expression and require you to look at these two fluorochromes on the same graph. So, therefore, to avoid this, we would suggest not to, as an example, choose CD3 in PE-Cy7 and CD4 in PerCP-Cy5.5 because those two markers will be co-expressed on the same cell, and when plotting these out, a user would encounter this kind of trumpet spread. With this knowledge in hand, I would recommend that users do some homework and perform a first compensation. Included here is a step-by-step guide to setting up the compensation and collecting it on our Cytoflex instruments. As recommended best practice, we would suggest users include single color controls, an unstained control, and possibly a single multicolor stained sample before your true experiment. Begin with, you would select which colors are in your panel and select beads or cells. Often beads are brighter and easier to stain and give a more consistent signal than cells. Set the gains to the recommended QC gains. This is important to do because the Cytoflex instruments will default to the last used settings, which are not necessarily the recommended QC gains. Run each single color control and compare the intensity of the positive peak with the spillover peaks in all the other channels. If there is too much overlap, make small increases in gain if those histograms are close to each other within twofold. If, however, the histograms are greater than threefold different, then the gains would not need to be adjusted. Carry over any gain changes as you progress through your single color controls until you finish collecting all of your controls. With these finalized set of gains, re-record all of your single color controls and your unstained control. Calculate your compensation and confirm that no value is approaching 100%. Save the compensation and the gain settings for future experiments and check your multicolored sample to see how the gating strategy and your compensation work in practice. It is understandable that users might feel hesitancy or apprehension about collecting their compensation for the first time, and our recommendation would be not to panic and not to let compensation intimidate you. Cytoflex instruments have a compensation process and template which organizes it into a more understandable way. I would recommend that users watch the video to get an idea of the process and how much difference between a positive staining peak and a spillover staining peak in a neighboring channel will lead to a result that is acceptable for compensation, and what level of changes to the gains can be made to conservatively increase the positive signal to then reach this acceptable compensation. Finally, if a user has questions, definitely ask the flow cytometry core and ask us for help, and we can provide assistance for settling on appropriate compensation and set of gains. This video was recorded on one of our Cytoflex instruments, and although I am slightly off with which log tick mark I'm at, the differences in relative intensity between the positive peak and the spillover peaks are what is important. All right, this is a test recording. This is a test recording for the compensation setup on one of our Cytoflex instruments. This is Cytoflex Oscar. We have the Site Expert software. To do this, we actually created a new compensation. I can actually just save this and go through the process of going through a new compensation. We have to save it as a file. We'll save this as this file. The compensation then requires selection of beads versus cells. Today this is going to be all beads. And we're going to do a 13 color. We're going to do all the colors for the compensation. The instrument creates the new experiment, and it creates histogram windows for all of the colors involved, with a sizing gate to find your beads and a histogram intensity gate to find the peak intensity for the bright positive cells. We have an unstained bead control in here, which then will be used as a negative peak. But first we're going to start with, at the beginning, with our FTSE control, which is in the first blue channel. Once I find it. FTSE, the first FTSE control. Importantly, to start with the default or with the recommended acquisition settings. These are the settings set by QC. Most likely the KO525 is going to be a bit too low. I would recommend, if it's, usually it starts at around anywhere from 30 to 40, to increase that up to 120, because by the time we get down there for the BV510 or the live dead, that we will have to increase that. We're going to run our sample first. We're going to run through all of the samples. We're going to make our small adjustments to our gains. After that, we will then go back and then re-record all of the samples with the final adjusted gains. Here we can see, if we focus on our beads, we can see our positive peaks in blue and our unstained beads in red. We confirm that the peak here for the channel we are recording, FTSE, is the brightest peak, and that nothing else comes close or overlaps. So right now this is at approximately about 3 to 4 times 10 to the 5th. The closest other signal is PE, which is at 1 times 10 to the 5th, and nothing else approaches close. So this setting of gain of 165 is fine for PE. We stop and we move on to the next one down the list. We set this gain as default. Any adjustments we actually made that KO525 gain. We'll go on to the next tube. We recall our default, the settings then, any changes that we've made by just clicking the default. And now we will run it. And we're going to go through then every tube in order. This is just adjusting the window. So we can see here, this is right below 10 to the 6th. The next closest would be the ECD, but that's at about 2 times 10 to the 5. This setting for PE, again, is fine. There is no significant overlap. So we can move on to the next tube.
Increase the speed a little bit. So we can see that the per CP is close. It is not overlapping. So the question might be, if that's not overlapping, do we need to increase that? We can select the gain hand and make a small adjustment, or we can increase it here. We reset that. Check the rest of the markers. But it was a conservative change. Because we made that conservative change, we have to change the default so that now that reflects both the change to ECD as well as that original change to the BV510. Now we have to recall the default to bring this up to 250 when we run our next color, the per CP. Again, this looks like it's the brightest. PESI7 is actually below 10 to the 5. This is above 10 to the 5. This per CP looks fine. One's a little wide, but the intensities are okay. So the ones to look out for are the APC 700 off of APC, right here. But this is high enough. The APC is clearly distinguishable from APC 700 and APC 750. So this setting is appropriate. So this is why we suggest when creating a new compensation is to start from the recommended settings. The recommended settings for most of these markers are appropriate and work with the stains. And always remember, click on your default. Click that. Restart. So now let's compare this. Likely is going to be close to 750, but 700 is still at a different level than 750. Let's try that. Check 660, check 700 in APC. This looks fine. So some of the main instances of overlap are between PE and PE dazzle, and the three violets between 525, 610, and 660 channels. Those violets have a fair bit of overlap between each other. They have to have narrow bandpass filters, so that's where I expect to see a little bit of adjustments being made. Here we're starting with BB421, which fits into the PB450 channel. Again, click on default to make sure that we're there. Highlight the positive, and we can see KO is at about 2. This is at probably about 6 times 10 to the 4th. This difference is likely, okay, it'd be about a 30% compensation, which is fine. Really, we're shooting for anything compensation to be under about 70%. Because there is some overlap that you cannot avoid, which still makes about a 50% compensation. Run. Other errors that you can encounter when running compensation is just loading the wrong tube. Okay, so this is right around 2 times 10 to the 5th. We can see it's actually still above 610, 660, 450, 780. This is perfectly usable gain setting. Change the default. Get that small change. Now we're on Violet BB605, I believe. Times 10 to the 5. We check. This is a little below 10 to the 5. It's at probably about 8 or 9 times about 8, 10 times 10 to the 4th. But this is still a sufficient difference. So we have 2 more tubes, and then we're going to calculate the compensation.
So you want to count visually manually so that
So is that right about 10 to the 5th? Below 10 to the 5th? Below. Definitely below. This will be a close compensation, but I always recommend to be more conservative in changing, because gains can tend to just creep up and get very high. And it's better to try it out at the original gains and then see if they work. So this is more, so this is a problem right here and right here are more than the 780. So we will need to increase the 780 intensity. You can either do it through here, or you can use the gain hand and drag it positive. Restart. So we can see here that this is now at 2 times 10 to the 5. This is still pretty close. How did that adjust it? That increased it to 400. You want to pull that maybe a little bit more positive. 500. 1, 2, so we got 3. This is at about 1.5. That's at a little below 1. So let's check the other closest ones to overlap. We would want to reconfirm that 660 ACE, the problem channels, or the other possible overlaps, 700, 750, and 660 aren't overlapped back into it. So we can, now that we made that change, we set these new gains as default. Let's quick check 660. Or actually, let's go back and to 700 and run it, overwrite the data, and use the new value for Violet 780, and then see if that has affected the compensation, the spillover intensity. So now this is still at 1 times 10 to the 4. 780 is still 10 to the 4, so that's fine. .780 is still below 10 to the 5, so that still works. So the most direct marker that will have the potential for a new overlap is Violet 660. For this we may have to increase. So 780, it's slightly below. This is a little bit above. I probably would recommend just a nudge up. I'm just basically going to trying to shoot for the first tick. So in the end, it's a 208. So we will save that as our default and make one last check. So 660 is still below 610. We know we're going to have overlap there. So these should be good. These final gains, default gains, can now be the ones that we will ultimately run our 13 color experiment with. So we can go back, and now we can re-record everything, starting with our unstained beads. We'll record 5,000 total events in each channel. One thing I would like to show is the actual calculation. That this is then applied so that if this is a 60% overlap between APC 750 and 700, what does that look like? Here is 700 and here is 750. This difference, this peak is 60% the intensity of this peak. So like I said, approximately about 4 times 10 to the 4 versus 8 or so times 10, 7 to 8 times 10 to the 4. That's where this 60% comes from. This compensation would be usable and would be good using these settings for any 13 color experiment that you would use with these antibodies.
Now that you've had an opportunity to watch the video with doing actual compensation on the Cytoflex, we can take a look at the menu and some of the options. This slide shows the menu options under the settings, which would identify compensation setup, the compensation calculation, and eventually bringing up the matrix itself. This is from a different compensation, so this one was only 4-color, FITSI, PE, APC, and APC Cy7. In here, we're looking at the APC Cy7 after compensation, and we can see the positive peak labeled in blue and the negative peak, in this case, labeled in green. We can see, if we go into more detail, an example of overlap from another compensation between the KO525 channel and the BV605. This would be Live Dead Aqua in the KO525 and BV610 in the BV605 channel. Both Live Dead Aqua and BV605 in this case are at 4 times 10 to the 4 intensity when running the control. And with the gains as they are set here for this experiment, the Live Dead Aqua spillover would exceed 100% into BV605 during compensation. These are the red arrows highlighting the relative intensities of the Live Dead Aqua when collected in the main channel, KO525, and then the spillover into the BV605. As the next step, if we would see this, we would then increase the gain in the Live Dead Aqua channel in order to create separation between it and BV605. After this has been done, the Live Dead Aqua is now reading out at 3 times 10 to the 5th, while the BV605 remains still at 4 times 10 to the 4. However, note the star that the background in the Live Dead Aqua channel has also gone up the same amount along with the signal. This is notable because one of the ways in which users overdo compensation is because they're looking for really large differences between your positive peak and your spillover peak, which is not necessary. They're looking for a tenfold shift in some cases between neighboring channels where, because of that previously identified spread, it is hard to get that amount of difference unless you really ramp up the gains. The problem then is that changing the gains changes both the positive and the background staining, and you end up with an experiment where your gains are all very, very high, as you have to adjust the gains for multiple other channels in order to account for this increased background spillover being carried over into multiple different channels. Often the compensation still does not look good with these very high gains. It is better to do small conservative changes. Don't shoot for 1,500 or 2,000 in your gains unless the QC has already set it at that level. Here we can see the finalized compensation for this panel, both before and after we increase the overlap between KO525 and BV650. An increase of the gain for the Live Dead Aqua in the KO525 channel has effectively reduced the spillover into BV605 from 120% down to 21%. However, because we increased the gain of the Live Dead Aqua channel, now when we read out the VIO blue marker, it is reading out a higher signal intensity in Live Dead Aqua. This results in an increase of the overlap from 15% up to 85%. If I were to do this compensation again, I probably would not increase the KO525 as much because, as I said before, trying to hit a tenfold difference in the amount of spillover between Live Dead Aqua and BV605 was not necessary. Another question that users might have is why adjust the Live Dead Aqua gain up rather than the BV605 gain down? This is because QC sets the gains at the minimum value for detection of a dim signal above background, and there is still room above the QC gains where the signal-to-noise ratio remains the same. Decreasing the gain for BV605 may drop that value below where you can detect a dim signal over noise. In this sample of a gain titration on the instrument, we can see that QC set the gain at 600, where P2 peak can be resolved above background. However, if we drop the gain from 600 down to 200, we lose resolution, and the P2 peak merges into the dim peak background. However, increasing the gain from 600 to 1250, the signal-to-noise ratio between two peaks remains the same. Investigations of differences in gains on both Cytoflex instruments have been performed, and they're available to look at. The relative coefficient of variation for, in this case, peak 4, we can see remains relatively constant over a large range of gains. However, below minimum gain value for each of the detectors, the RCV value increases substantially as the detectors have a difficult time identifying photons from background noise and dark signal noise. There is a maximum gain value beyond which the increasing the gain does not improve the signal to noise value in a meaningful way. This does not mean that gains can't go higher, just that gains that are higher, in this case of 600, will increase the signal, but also increase the background by an equivalent amount. For compensation experiments, it is recommended that users should reacquire all the channels after changing the gains of one marker. Running all the samples with the same gain settings will help confirm that there is no overlap, and this is best practice for compensation experiments. Although Beckman suggests that its detectors are sensitive enough and that they have defined how these changes will affect the compensation, it adds a trivial amount of time for you as a user at the beginning of your experiment to quickly confirm that a final set of gains will work for your antibodies and will not create any substantial overlap, and that the compensation settings will then be acceptable for your experiment, because users will often reuse these settings and gains over and over again as our instruments are relatively stable in the gains which are set by QC. So an investment of time at the beginning of the experiment will help produce reliable settings for all of your repeats. In summary, while compensation may seem like an arcane art, it really is just subtraction. It is a software correction for spillover as fluorescent markers are detected across multiple channels. Compensation is calculated by testing how the gain settings for your single color controls record spillover into adjacent channels. It is important for users to compare the peak intensity of your single color controls with the spillover intensity in neighboring channels. And if the spillover intensity is too close, to conservatively adjust your gain upward. Changing the gains will change your compensation. It is important for users to internalize this. And while compensation can be tweaked after collection because it is layered on top of the raw data, it does not actually change the raw data. Gains cannot be changed after collection. And starting with a correct set of gains will produce the best experiments and the most interpretable results as possible.